All right, number 23 says, when a truckload of apples arrives at a packing plant, a random sample of 150s is selected. So, what's that number? N, right? N is 150. And examined for bruises, discoloration, and other defects. The whole truckload will be rejected if more than 5% of the sample is unsatisfactory. Okay, so it's rejected if p hat, the probability or the proportion of bad apples, is greater than 0.05. Suppose that in fact, 8% of the apples on the truck do not meet the desired standard. So the proportion of bad apples is actually 0.08. What's the probability the shipment will be accepted anyways? So what's the probability that the p hat, the sample, will actually be less than 0.05 and it won't be rejected? Okay. So we need to check our conditions. The sample is random. They tell us that. 150 is less than 10% of all the apples. Okay. And then 150 times 0.08, greater than or equal to 10. Do we expect more than 10 bad apples and more than 10 good apples? So that's 12. Remember, it can equal 10. 0.92 is 138. Okay, so conditions are met. A normal model is appropriate. Okay, so my normal model has a mean of 0.08 and a standard deviation of the square root of 0.08 times 0.92 over 150. Right? The square root of PQ over N is our standard deviation calculation, and that gives me .038. So when the book is drawing the normal model, to give us a visual representation of what we're finding. The mean of this model is 0.08. The standard deviation is 0.038. Oh, that's not right. I put in 50 instead of 150. It's actually 0.022. Okay, so it's 0.08 minus 0.022. That's 0.058 minus 0.022. 0.036 minus 0.022. 0.014. Now 0.08 plus 0.022, 1.102, 0.124, 0.146. Okay, so the question was, how does the book decide where it's shading? Caleb.
Do we have to write in that N format all the time?
You should. You should, because you've described the shape, the center, and spread of the distribution. So it shows that you understand what shape you're using. You're using a normal model and what the mean and the standard deviation is. So it's a good habit to get into, defining your model. Okay. Now, the question was, what's the probability that even though 8% of these apples are bad, when they do a sample, they accept the truck because less than 5% of the apples in their sample are bad. So what's the probability that the sample proportion is less than 0.05? That's where it's choosing where to shade. 0.05 is about here. And I need less than 5% of the apples in my sample to be bad in order for the truck to be accepted, and they bring it in and then they sell them. Yes. So my z-score is 0.05. the sample proportion I'm interested in, minus the actual proportion. Now, you're not always going to have the actual proportion, and we talk about that in the rest of the semester. Okay, very rarely do you know the exact number of bad apples in the truckload. You're using the sample to determine whether you should accept it or not. And that's 0.022. So negative 0.03 divided by 0.022. Now, one of the benefits of looking at the model is it shows us that my z-score should be less or bigger than -1, right? Or less than -1. Because my 0.05 is more than 1 standard deviation from the mean, right? And it's below the mean. So it's kind of a self-checking thing. When you draw the picture, you can see about how many standard deviations. It's somewhere between -1 and -2 standard deviations, the 0.05, right? So when I do this calculation and I get a positive, it should be like, oh, wait, I forgot about that negative sign because this is below the mean. And we get negative 1.3636. And then we do normal CDF, negative 99, comma negative 1.3636, because it's less than, right? So I want this area. I want from negative 99 standard deviations all the way up to this, which is negative 1.36 standard deviations, right? It's not greater than would be my z-score, comma 99. And so negative 99, comma my answer, and I get 0.0863. So there is an 8.63% chance that the truckload will be accepted even though 8% of the apples don't meet the standard. It's the probability of getting a sample less than 5% if 0.08 is the actual proportion of bad apples in the truckload. Questions on that one? Yes, Jacob?
So why does the sample have to be less than 10%?
So it's less than 10% because we know that we're not sampling without replacement or with replacement, right? We're not going to take an apple and say, okay, it's good, and then put it back in. That would be clear independence, right? We choose less than 10% because if it's less than 10% of the population, even though we're sampling without replacement, we're not changing the amount of apples that are in the truck by enough to affect the probability and the percentage a lot, right? If it's more than 10%, then we're changing the probability, right? Think about your deck of cards. The first card, it's 4 out of 52, and the next one's 4 out of 51, and the next one's 4 out of 50. So that denominator's changing. But if we have 15,000 apples, the difference between 1 out of 15,000 and 1 out of 14,999 is not that big of a difference. So the difference in that probability, because we're selecting without replacement, isn't enough to cause it to really change. And so we can assume that the probability will be really similar if you were to do it with replacement. Okay? And then number 25. 25 says, while some non-smokers don't mind being seated in a smoking section of a restaurant, about 60% of the customers demand a smoke-free area. Clearly, this book is old because I don't even know if this situation exists anymore. It doesn't exist in this state, but I don't even know, even out of state, if they have smoking sections in a restaurant anymore. When I was little, you would go to a restaurant and they would ask you smoking or non-smoking. And my dad was a smoker for a while, so then he would say smoking. And we would sit in the section where you were allowed to smoke. And then my dad stopped smoking. And then we started sitting in the non-smoking section, but you could still smell the smoke from the non-smoking section, right? So eventually they banned smoking in restaurants. But it used to be a thing. They had a specific designated area inside the building that you were allowed to smoke at your table. So about 60% of customers demand a smoke-free area. A new restaurant with 120 seats is being planned. How many seats should be in the non-smoking area in order to be very sure of having enough seating there? Comment on the assumption and conditions to support your model and explain what very sure means to you. Okay, so the proportion of people that definitely are going to want non-smoking is 60%. Our sample size is 120. Okay, so conditions. We're going to say that the 120 diners is going to be, on any given day, is representative of their clientele. It's clearly not a random sample. You're not like randomly picking people to come have dinner. We say 120 is less than 10% of all prospective diners. Of all the people that chose to go out to dinner that night, it's probably more than 1,200 people, right? So that's less than the 10% that could choose to eat there. Not to mention, they are cycling through those 120 seats, right? People finish, they clean the table, more people come in. So less than 10% is fine. Now 120 times 0.6 is 72. And 120 times 0.4. This is our NP and NQ has to be greater than or equal to 10. This is the condition that checks to make sure the sample size is large enough. That's 48. So since conditions are met, a normal model is appropriate. So let's create our normal model. 0.6, square root of 0.6 times 0.4 over 120 is our standard deviation. And that's 0.6 and 0.045. So we are going to draw the normal model here. If I want to be very sure, right, I should have 2 or 3 standard deviations from the mean, right? Because we expect there to be 60% of the people to want non-smoking, but that's not going to be the exact same every night. It's going to vary. Some nights you're going to have more people wanting non-smoking and less people wanting smoking, and some nights you'll have less than the 60%. It's going to vary, and that's what that standard deviation is telling us. How much do we expect it to vary? And if we want to make sure we cater to the people that want non-smoking, how many seats should we have? Probably that 95% mark, right? The 2 standard deviations, 0.645, 0.69, 0.735, and 555. 0.51 and 0.465. So your 95% mark, 95% of the time, they expect between 51% of their customers and 69% of their customers to want a non-smoking seat. Yes?
Would it be okay if you chose 3?
Yes, it's okay to choose 3 standard deviations as well, right? Because remember that this is about 2.5%. Okay, so 2.5% of the people don't get. If you want to be extremely sure, if you go to the 3 standard deviations, remember that's about 0.015%. You're definitely not going to have you know, you're really, really safe at 3 standard deviations. You're pretty sure you're pretty safe at 2 standard deviations, right? So, but it asked how many seats. So saying 69% or 73.5% is not how many seats, right? So 69% of 120 is 82.8. So you would say 83. And 73.5% of 120 is 88.2. So 89. So either 83 or 89 seats for the non-smoking section would be very sure to have enough. And you can justify that by saying 95% of the time it's going to be below, or like only 2.5% of the time will more than 83 people ask for that. Or we expect only 0.015% of the time more than 89 people ask for non-smoking. Okay, so you can justify that by saying 2 standard deviations is very, you know, only 2.5%, or 3 standard deviations only 0.15%. 0.15 or 0.015? I think it's 0.15. Yeah, 0.15%. Okay. We talked about proportions, the sampling distribution for a proportion. What about the sampling distribution for the mean? And the number one question I get about this is, how do I tell if it's a proportion or a mean? Well, if it's a mean, it's going to say the mean is, and the standard deviation is, this and this. If it's a proportion, it's going to give you a percentage, or this 566 out of 603. It's going to give you a proportion or a percentage, or it's going to give you a mean and a standard deviation. So, as we did with the sampling model for proportions, we're going to use the central limit theorem together with 68, 95, 99.7 rule and normal percentiles to examine what the mean of samples drawn from various populations might look like. SAT scores should have a mean of 500 and a standard deviation of 100. What do we expect the mean and the standard deviation to be for a random sample of 20 students? Okay, so remember that a sampling distribution means I'm picking 20 random students and averaging their SAT scores. What do I expect the new mean and standard deviation to be? So for A, the mean is still 500. My formula for the standard deviation of the mean, the sample mean, is sigma over the square root of n. The question is, are you given sigma? Then you can use sigma over square root n. If you have to calculate the standard deviation using square root pq over n, you should not be using that for this formula. Right? You're using one or the other. We don't combine them. So that would be 100 over the square root of 20. So the normal model, 500, 22.36. Now, that's what the normal model would look like if it were appropriate. Is a normal model appropriate? Well, SAT scores are normally distributed. Okay. If you are drawing from a normal population, then your sampling distribution will be normal no matter what the sample size is. So it might tell you that this is normal, normally distributed. That is I'm allowed to use the normal model because it told me it's normally distributed. We need to use the central limit theorem when the population is not normally distributed. Because we have to be able to say my sample size is going to be large enough so that my sampling distribution will be normal even though the population is not. I'm drawing from a population of speeders and the average speed on the road. That is definitely not normally distributed. It's skewed to the right. you don't have very many people driving 10 miles per hour on the freeway, they'd get killed, right? Your distribution is you got a lot of people driving around 70, right? You have a few that are in the 65, 50 range, and you're like, God, get out of the fast lane. And then you've got your people that are driving 90 and 100, okay? So, oh, what just happened? Our conditions are less necessary when the population is normal. What just happened? Okay, so again, it tells us a random sample. Okay, that still has to be true. The sample has to be random. Less than 10% has to be true. 20 is less than 10% of all students who took the SAT. And the population is normal. So we can use the normal distribution. We'll talk about using the central limit theorem in the next two. So what does it look like? 500, 522, 544, I'm just going to round, 566, and 478, 456, and 434. So 68% of the time, the mean of 20 students will be between 478 and 522. Now that's not an individual score, right? The standard deviation for an individual score, your individual score and knowing your percentile, that standard deviation for one single person is 100. So 68% of the time, your score is between 400 and 600. 95% of the time, the scores are between 300 and 700. And 99% of the time, the scores are between 200 and 800, and is actually 100% of the time because you can't get less than a 200 and you can't get higher than an 800. You get a 200 just by putting your name on the SAT. Yeah, the scores are between 200 and 800 because 800 is the highest you can get. Well, yeah, how are they going to give you any points if they don't know whose it is? But if you're submitting a 200 to colleges, they're going to be like, you might not be a candidate for us. You might as well have just left it blank. So, but this we're talking about taking 20 students and averaging their scores. So, and the more students you take, the bigger the sample size, the lower the standard deviation is going to be because it's going to be less spread out when you take the mean of a higher number of students. So 95% of the time, that sample mean will be between 456 and 544. And 99.7% of the time, it'll be between 434 and 566. And you can write those sentences. B, speeds of cars on a highway have a mean of 52 and a standard deviation of 6 and are likely skewed to the right. Describe what we might see in a random sample of 50 cars. So the mean is 52 and sigma is 6. Highway, not freeway. There's a difference, right? You guys know the difference? Highways are like 2 lanes, you know, going up the mountain. Freeways out here have like 18 lanes sometimes. Like in the middle of LA with 4 freeways converge on each other, there's like 10, 12 lanes, including the HOV lanes. So, so our conditions. Sample is random. $50 is less than 10% of all cars. And 50 is large enough. Remember, our threshold for large enough to apply the central limit theorem is about 25. Okay, to apply the central limit theorem. So since conditions are met, a normal model is appropriate. So what is my normal model? The mean is 52. The standard deviation is 6 over the square root of 50. Central limit theorem, remember, says even though the population of speed on the highway is skewed to the right, if my sample size is large enough, I pick 50 cars, I find the mean, and I put it on a distribution, in a dot plot, in a histogram. I find another 50 cars, find that mean. That distribution is going to be normal, even though my population distribution is not. Okay. And so that's 52, and 6 divided by the square root of 50 is 0.848. So what might we see in that random sample of 50 cars? Big difference from using 6, right? We're using 0.848, so we're going to use 0.8. 5 to 0.8, 53.6, and 54.4, right? And then subtract it, 0.512, 0.512. Oh, yeah, you're right. I was converting it to a decimal, right? 51.2, 50.4, and 49.6. Yes? No. Well, you have the standard deviation of the population of cars on the road. So cars, if you pick a random car, a single random car, they have a mean of 52 with a standard deviation of 6. But if I take a sample of 50 cars and find the average speed of those 50 cars, that mean, right, I'm taking a mean of the 50 cars and a mean of 50 cars, that distribution of a sample size of 50 has a much smaller standard deviation of 0.848. So I have the mean, the standard deviation of the population, but that's not the same as the standard deviation of the sample mean. I'm taking a mean of 50 cars, right? If I took 5 students in here, I took your GPAs, right? If I could create a model for the GPA with a standard deviation for this class, right? Find everybody's mean and standard deviation, or everybody's GPA, find the mean and standard deviation. If I take 5 of you and average your GPAs, that's going to vary less than a single value because I'm taking a mean of 5 people. When I take a mean, it balances out some of the variability. I could have someone with a 4.5 and someone with a 3.0. Well, that's not going to vary as much once I take the average of those because it takes out those outliers. That way? Yeah. So in a sample of 50 cars, we expect the mean speed to be between 51.2 and 52.8, 68% of the time. 95% of the time, the mean should be between 50.4 and 53.6 miles per hour. Okay, with means and standard deviations, it's important to put the units. And 99.7% of the time, the mean should be approximately between 49.6 and 54.4 miles per hour. So as soon as the sample size changes, there's a new standard deviation for the sampling distribution. Sample size of 100, it's going to be a lot different. It's going to be 0.6, right? Because 6 divided by the square root of 100 is 6 divided by 10, 0.6. If I do 200 cars, standard deviation is going to get even smaller. Okay. Questions? And the last question, C. At birth, babies average 7.8 pounds with a standard deviation of 2.1. So mu is 7.8 and sigma is 2.1. A random sample of 34 babies born to mothers living near a large factory that may be polluting the air and water shows a mean birth weight of only 7.2 pounds. Is that unusually low? So the sample mean is 7.2. The sample size is 34. So we want to know, here's the application. They do know the average birth weight of babies with the standard deviation in every state and every country because they gather that data when the baby's born, right? And they keep a database of it. So if they want to know that a certain factory is it affecting birth weight of babies, we want to know if I take this sample of 34 and I find the average, is that unusually low enough for us to say this factory is causing harm? Okay. So my normal, my conditions, it's not a random sample. Oh, it is a random sample. Sample is random. 34 is less than 10% of all babies. And 34 is large enough to apply the central limit theorem. So conditions are met. A normal model is appropriate. So our normal model is 7.8 and 2.1 over the square root of 34. If you are given a sample size, you need to be using sigma over square root n. Yeah.
What do we do with that second mean?
We're going to use it in our z-score calculation. Because we're going to it's asking what's the probability that the mean, the sample mean for these 34 babies is less than 7.2 pounds. Okay, or we want to know, is it unusually low? So is it a lot of standard deviations from the mean? We don't always have to have the percentage when it's asking unusually low. We can base that calculation on the fact that more than 3 standard deviations from the mean is really unlikely, and so is more than 2. So my normal model is 7.8, 2.1 divided by the square root of 34. is 0.36. So instead of drawing the normal model, I'm going to calculate a z-score. My sample mean, x bar, is 7.2, minus the population mean, 7.8, divided by the standard deviation of the sampling distribution. So negative 0.6 divided by 0.36 is negative 1.667.
CLT is about 25.
What? CLT about 25. More than 25, you can say it's large enough. Then we can say normal CDF. It would be negative 99, negative 1.667. Now the question doesn't actually say what's the probability that's less than 7.2 pounds. It's asking for unusually low. And we can say right here after our z-score is only 1.67 that no, it's not unusually low because 95% of the time the average will be within 2 standard deviations of the mean, and this average is within 2 standard deviations of the mean. Okay, so we can say no, it is not unusually low, because the mean of 7.2 is within 2 standard deviations of the mean, which occurs approximately 95% of the time. If you did your normal CDF, we actually get a percentage that's not as large as we would think. We get 27%. There's a 27% chance of getting a mean 7.2 or lower. That's not that unlikely. Oh wait, no, that's the wrong number. Hold on. That didn't make sense to me. I had the 0.6 in my calculator, not 1.667, and I used the answer. 4.7%. Okay. It's still within that 2 standard deviations, so either argument could be accepted as okay. And here's where statistics gets fun. If I'm using the 2 standard deviations rule, no, it's not unusual. But if I look at the percent, there's only a 4.7% chance of getting a sample that low or lower. Is that low enough for you to say, yes, it's unusual? It's kind of a judgment call. And we'll get to where we set a standard for that judgment. We set that standard at the beginning of the problem and say, okay, if it's less than this percentage, we're going to say, yes, it's unusual. And if it's above this, we're going to say, no, it's not unusual. And that percentage is usually 5%. Okay.